Here's another example out of the book. Example 4. And again, I want to illustrate the strategy and talk about how this is a little bit different from example 3. Draw a diagram. So you should read this and pause it and read the problem, because I don't want to read the problem to you. You can read. Example 4, we've got this car, 2 cars moving, and they draw a diagram. Ooh, can't see that. They draw the diagram, and we've got a right triangle. Okay, sounds like Pythagoras is probably going to be our master equation. And what's really different about this is that they're given 2 rates of change. Car A is traveling west at 50 miles per hour. Car B is traveling north at 60 miles per hour. So any kind of velocity information, that's going to be a rate of change. It's a rate of change of a distance. And one thing that I mentioned in class is that when you have motion, for us it's almost always going to be straight line motion, because any other kind of motion is going to be a little more too complicated for us. And you're going to be able to draw the line of motion, and if you're looking at a velocity and you're wondering, how do I get that in, like 50 miles per hour, how do I get that into this thing? How is that a rate of change of something I can draw? You want to think a velocity, if you're talking about straight line motion, a velocity is the rate of change of the distance between the thing that's moving, the car, and some point on the line of motion that isn't moving, that's fixed. And so here it is, the intersection of the 2 roads, that's going to be our reference point for both things. So you want a reference point for motion, and it's going to be a point that's not moving along the line of motion. Luckily here, this point works for both of these guys. So it's not luck, but it's what makes the problem work. So that's something that I've learned how to say in an explicit way after teaching this for a long time. Okay, so we've got these quantities: x, the distance from A to the intersection; y, the distance from B to the intersection. And what they're asking is about at what rate are the cars approaching each other. It's that diagonal distance. Remember, when they say a distance between 2 things, if they don't modify it with like horizontal distance or distance to a point on the ground under or something like that, it really means the straight line distance. We saw that in the radar problem, for example. So here's the explicit numbers. They've translated the traveling west and traveling north into minus 50 and minus 60. There's those signs again that are really crucial. These are decreasing. When you draw the picture, you always want to ask, okay, is this quantity here decreasing or increasing? I'm going towards the reference point. That's going to be a decrease in distance as time goes forward. Now, the master equation is z squared equals x squared plus y squared. But here's the real key thing here, that we've got 3 quantities. We had 3 quantities in the water tank problem, but 2 of them, R and H, were completely linked together. They weren't really independent quantities, and in fact we found the precise relation using similar triangles. Here, x and y and z, or x and y, are really independent of each other. This guy could speed up or slow down if he wanted to. This guy could speed up or slow down. They're not linked in any necessary way. So you're never going to get an auxiliary equation here that links x and y. So if they had only given us dx dt and not dy dt, there's no way we could do this problem. We need to know about how fast both cars are moving. These, in a way, are the easier kinds of problems. They're giving you, there's a relationship between 3 variables, and they go ahead and give you all but one of the rates of change. And that's the thing to look for, and that's what I'm talking about in 4a. If all but one rate of change of the multiple quantities, more than 2 variables, if all but one rate of change is given explicitly, then you don't need to look for an auxiliary equation. Don't try. You don't need it. Just go ahead and skip to 5, the key calculus step, differentiate the master equation. Again, using the chain rule. Every single variable, every single one of these z, x, and y, they're really functions of t. They all get a chain rule factor. And you can solve for dz dt, and then you need to plug in all your quantities. Another thing that's crucial, and it's very common in these 3 variable problems, is that they give you x, that's the car A distance, and y, that's the car B distance, 0.4. So those you're given. They give you dx dt and dy dt, those are given. They don't give you z explicitly. And that's what I mentioned about here in step 7. You will often have to go back to the master equation. Well, you can't even remotely see that. You will often have to go back to the master equation to determine values for all the quantities. They don't have to give you z independently, because if they give you x and y, then z is determined out of that. And so, let me move this up. So you do actually have all those values, but you did have to go back to the master equation one more time. So in general, if you're stuck, go back to the master equation. And there's your dz dt is minus 78. Okay, so that's 2 examples of this process, and that should be good to get you on your homework.